just like in Calculus 1, all the terms that don't involve delta whatever, in this case delta y, are going to cancel. And of course, it's the same problem as in Calculus 1. Oh, we're dividing by 0. If we were to let delta y go to 0 now, we'd be dividing by 0. That's no good. But all the terms that don't involve delta y cancel, which means that all the terms that are left do involve delta y. We factor it out. It makes it easy to divide by delta y that way. So delta y into there is going to give me 10x squared y. Into the other one, I've got 5x squared delta y. And now I take the limit, and I get 10x squared y plus 0. That's the derivative. And for the other one, d sub x f of xy, that will be a limit as delta x goes to 0. And over here, I've got the x cubed plus 5x squared y squared, subtracted. And now, for the x cubed, let's see, x plus delta x cubed and 5x plus delta x squared times y squared minus delta x. And either you know the binomial formula or you don't. If you don't, that's okay, because I'm going to write it down. When you square a binomial, you get 3 terms. Second power, you get 3 terms. Third power, you get 4 terms. And it's going to be, anybody want to help me out here? X cubed plus, you don't know that. X squared delta x, but there's a coefficient.
Oh, 2.
Well, for squares, it was a 2. This is a 3. You got it. And
Delta x cubed.
And I'm seeming to write upwards. But anyway, 5 x squared y squared, because I'm going to multiply that in, plus 10 x delta x y squared plus 5 delta x squared times y squared. Oh, and I have these others, minus x cubed and minus 5x squared y squared. All the terms that do not involve delta x are going to cancel. Wow. Whatever. Gone. Gone. So all the terms that are left do involve delta x, which makes it easy to divide by delta x. That's only valid for polynomials. You do trig functions and all that stuff, that's a lot tougher. But anyway, so I'm going to get 3x squared, the delta x cancels. One of the delta x's cancels up here. And over here, the only delta x in that term cancels. And we have a 5 delta x. I'm going to put the y squared first. 5y squared delta x. And no denominator. So now we just simply let delta x x go to 0. 3x squared plus nothing plus 10xy squared plus nothing. So my answer here is 3x squared plus 10xy squared. Now, those of you that have not done cubes of binomials before, well, let me just say, I bet you have and don't remember. But anyhow, here's how it works. I mean, okay, there's that triangle, you know. But forget the triangle. There are your coefficients for the thing, but where did those coefficients come from? Pascal's triangle, yeah. Same guy with the toothache. And, but if I have x plus delta x, yeah, x plus delta x, and I write it 3 times.
I need the one for square. I just didn't know.
What now?
I need the one for square. I didn't know the one for cube.
Yeah, well, I would hope that everybody knows the one for squares, because you're supposed to pick that up 8th or 9th grade. But anyway, how many terms do I get before I combine everything? I got 2 terms times 2 terms times 2 terms. Would it be as simple as saying 2 times 2 times 2?
You wish.
It is.
It's all.
So I've got,
It's a
like say, x times x times x, or I could do x times delta x. Or I could have x times delta x times x, or x times delta x times delta x. So all the combinations, there are 8 combinations. Combinations is a loaded word, I know. I'm not talking about combinatorials here, although I'm real close to it. So anyway, we get x cubed, but also, let's see, here's an x squared times delta x, and here's another x squared times delta x, and here's another x squared times delta x. So I got 3 of them. Let's put it this way, x, delta x, x, and then I have delta x, x, x. But multiplication is commutative, so all those are the same. And then I do the same thing. Here is 1 copy of x times delta x squared, and there's another copy, and there's another copy. So I got 3 of those. And finally, delta x, delta x, delta x. So it's all very doable, and especially when you have the triangle involved. All right. Well, anyhow, forget the algebra. Let's look at the calculus. Naturally, we don't want to do these limits very much. In Calculus 1, they made you do, what, about 2 dozen of these things? Before you caught on? Well, I would like to think that you caught on before, but you still had to do them because you're supposed to do them. So we want to catch on here. After they made you do all those limits, then they said, well, you know, there's some formulas. There are formulas? Well, why didn't you show us the formulas? Okay, so here we go. Basically, you do the same thing you did in Calculus 1, but you assume when I'm doing the x partial, we assume that the y is a constant, because that's the way it is. So here we have, the x's are different, but the y's are the same. So if I'm treating the y as a constant, it's like if I'm doing x cubed plus 5x squared y squared. Well, how about if I let y equal 3? Then I've got x cubed plus 5x squared times 9, so that's x cubed plus 45x squared. I know how to do that. I get 3x squared plus 90x. Well, same thing here, only I don't know what constant it is. But it's a constant. X is changing, but y is just sitting there. So, looking at this thing, and I'm going to erase this. Looking at this thing, of course, I get the 3x squared. And don't you dare write equals without telling what equals, because f of x, y is not equal to that. So anyway, this is going to be d sub x f at x, y, or whichever notation you happen to want at the time. And then over here, I've got a great big old constant times x squared, so I'm just going to get the great big old constant times 2x. And that's going to give me 10x y squared, which should be what I got a while ago. Yeah, there it is. But when I do the y partial, d sub y f of xy, then I get, x is constant, x cubed is a constant. So I get great big old 0. And then, let's see, x squared is a constant. I'm just going to copy my constant, 5x squared, and then the derivative of y squared.
2y.
2y. You more confident now? 2y?
2y.
What about 2y prime?
What about it?
Explain what about it. A lot of people get mixed up about that business from Calculus 1. Oh, so let's see, we've got, like when we've got u squared, take the derivative, you don't just always get 2u. So if I'm doing, say, sine squared, I don't just get 2 sine x, I got to do 2 sine x times the derivative of sine x. Yeah, or 2u u prime. And y squared, is that any different? 2y y prime. But I didn't do 2x x prime. You don't do 2x x prime in Cal 1. And you don't do it in Cal 3 either. All right? There is no y prime here. It's a derivative with respect to y. Over here, this one is a derivative with respect to x. And so after you get done with that, you think, oh, well, but there's a chain rule involved. And we will have a chain rule thing later on. It's going to be much grosser than the one in Calculus 1. But anyway, so don't put those y primes in there. But if you do, then simplify. Let's see, what's y prime? Derivative of y with respect to y is 1. So y prime would be 1. Okay. That's the last limit I'm going to do as far as calculating derivatives is concerned. All right. Let's look at problem 2 on supplement 3. G of x, y, z equals x tangent y over 3y minus z squared. Number two. And it leaves it up to us what notation we use. In problem 1, I said del f, del x, and del f, del y, so I kind of expect the answers to be written that way. Here, we take our pick. I think I'll use the subscript notation. So let's do g sub x of x, y, z. That just means the x derivative. Same thing as saying dxg of x, y, z.
Can I ask a
Yeah.
question? On number
You already
3,
did.
on number 3, you see how it says like w like sub x? Is that the same thing?
That's the same thing. And it's just like calculus 1 again. When we have y equals f of x, then the derivative, we've write f prime of x, but we could just well put it on there. So the dependent variable can be mutilated in the same way that the function name can. Alright? Okay, so I'm gonna keep, let's see, what's constant now if I'm doing this derivative? Z and y. So everything's constant except that. I'm gonna pull that x out here, and then I just got this great big constant. I don't know how big it is numerically, but it's tall anyway. And so what do I get?
Just tangent y over 3 y.
Over all that was.
Right.
So I'm just taking derivative of x is 1, and I've got a multiplier. And then well, what about for y? G sub y.
Gross.
What? Gross?
Yeah.
Okay. Well, tell me about it.
You do, I guess, a quotient rule.
I'm going to use, I guess, a quotient rule.
You could.
In fact, that's the theme here. The same rules that you got in Calculus 1 work in Cal3, except the chain rule looks a little bit different. So anyhow,
Just gotta be careful.
you got to be careful. So I'm not looking at it this way, I'm just doing that. So I'm going to do the bottom times the derivative of the top, and that's a y derivative. I might even go so far as to put del y here, just like we sometimes do d dx when we're talking about these things. D dx of f of x. So if you get confused by having just d by itself over the dx, well, get used to it. But anyway, this just says take the y derivative of whatever that is. And so, what do we have here? X tangent y. And then we subtract the top times the derivative of the bottom, del y of 3y minus z squared.
All over the square.
All over the square. All around the square.
You sure you want to do that?
Oops.
Yay.
There we go. Am I sure I want to do that? Well, oh well, they're paying me. Pretty well.
If there was ever a reason to do something.
Yes, yeah, there we go. What's your motivation? All right, the theme here, and again, you got basically the same rules. So the quotient rule is going to work. Now it's just a matter of implementing it. So the bottom, now what's the derivative of x tangent y with respect to y?
Secant squared y.
Secant squared y.
Times x.
Times x, yes, okay. So a lot of people will, you know, if they had 7 tangent y, they'd get 7 secant squared y, but somehow that x just shrivels up and dies. So make sure you got that in there. Minus x tangent y times what?
Times 3. 0.
And then we'd want to clean it up a little bit, but not a whole lot. Should I even bother to multiply it out? I'd probably factor out the x. And then I would have 3y secant squared y minus z squared secant squared y minus 3 tangent y. Or however you want to do it. All over black.
I get lazy too. Sometimes I just draw like a squiggly line on the bottom.
Yeah, well. Do you have squiggly line privileges? I do. All right, so G sub Z of X, Y, Z. Quotient rule?
Which one?
To the Z derivative.
No.
No?
No.
Well, you're both right. You can do a quotient rule if you want to, but on the other hand, a lot of times when we have this kind of situation,
So the derivative of the top
we
is
think,
like zero.
yeah, the derivative of the top is 0, so we could just go ahead and do a -1 power thing.
Yeah.
So, and if I were doing the second derivative, if I already had a square down here, I'd certainly want to do a negative exponent. But anyway, in this case, it really doesn't matter one way or the other, but I just want you to be alert to the possibility. If there's no variable in the numerator, you can always do this kind of thing. So I just copy the x tangent y. Again, if I did the product rule, that part would give me 0 anyway. And I have -1, and that -1 is because we subtract in the quotient rule, right? I mean, it corresponds to that. 3y minus z squared to power -2. And then the u prime stuff, -2z. And let's see, I usually go ahead and put the answer back in the same format that the problem was given in. So since the original was given as a fraction without negative exponents, I'm going to go ahead and put it back in that format. So I'm going to have just the 2z, and there's an x tangent y, and of course I like alphabetical order, so I'll put the x and then the z. I don't want to put the z over here though, because that gets mixed up. Looks like tangent y, z. And then let's see, this stuff sinks to the bottom, and that's it. All right. So I had one that it wasn't real gruesome, and we'll certainly see more gruesome things that we have to worry about. But for right now, that was enough. Now I want to do a simpler one, but it has a little thing that people get messed up on all the time. So what if I have another trig function here? Oh, give me a trig function.
Secant.
Secant. All right, now you've put a lot of trig functions together. I'm going to go with secant. That's the first trig function. The other one was an inverse trig function.
Yeah, articles.
Yeah. Secant, and suppose I've got maybe an x out here, and inside here I'm going to have maybe x squared y. Okay? X squared y cubed. So here is f of x, y, and I'm going to do my partials. Let's do the y partial first, because that looks easier. So I've got del f, del, or I can't wait. If I give the thing a dependent variable name, if I call this thing delta, for example, then as you already noted on the handout, I could say,
I was just making sure that was
Yeah.
derivative.
yeah, so I can say del w, del y. So the x is a constant, and I take the derivative of the secant with respect to y. So it's going to be secant tangent, just like calculus 1.
The inside should stay the same.
And the inside stay the same. When you take the derivative of a trig function, you always get the trig function of the same angle. And now what about the u prime part?
Times 3y squared.
Times 3y squared.
3xy squared.
3xy squared. Well, you can do this x?
Yeah. Then just putting it up front and then I'll put it.
Yeah, oh, yeah, okay, so I cleaned it up, I moved that up front, but it's not right. What if it had been 5y cubed instead of x squared y cubed?
So 15.
So you get a 15. So this just goes invisible on you when it's a variable.
Oh, yeah.
3x squared y squared. And then you can clean it up.
Yeah, with that X multiplies by others?
I just put the x with the x squared. And well, it's still going on. Did that clock stop? All right. I want to look at problems 5 and 8. This thing. So I have x equals r cosine theta. And let's see, this is problem 5. And I want both partials. And number 6, I've got, oh, this reminds me of, what's those coordinates? Polar. All right. And number 7, I've got r equals the square root. That's also a polar coordinate formula. And 8, arctangent. Theta equals the arctangent of y over x. So all of these are related to the same picture. So here's xy, and there's r and theta. And if I drop this perpendicular, then this distance is y, at least in the first quadrant. Now the distance is not y if I'm down below the axis, but anyway. So I've got opposite over hypotenuse up there, adjacent over hypotenuse, opposite over adjacent, and then solving for whichever variable we want. So these are all the different ways of getting one coordinate in terms of the 2 from the other system. Anyway, let's have it here. For problem 5, I want del x del r. What's that?
Cosine theta.
It's cosine theta. So one of you sort of translated what it meant, the other one did the computation. I like that. All right, del x del theta.
It's the inverse cosine of r.
No, not the inverse cosine.
Negative r.
Negative r
Times sine of theta.
times sine of theta. So up here, r is a constant.
Just take root of the cosine.
Okay, and 6 to 7, you worry about them too. But y'all been chomping at the bit to do inverse trig functions, so let's look at problem 8. So I want del theta del x.
That's going to be 1 over 1 plus y over x squared.
And I assume you mean the whole thing is squared.
Right. Times negative y over x squared.
Very good. Just rattle it right off. So what's going on here, if I have arctangent u prime, I get 1 over 1 plus u squared times u prime. And so when he wanted to look at the u prime here, said, oh, that's a negative, yeah, that's y times x to the negative 1. And so we did minus y times x to the negative 2. Now let's simplify it. So I've got 1 times negative y is negative y. And I have x squared times 1.
X squared plus y squared.
X squared plus y squared. So,
That's not so good.
not so bad. All right, now, one of the themes of this part of the partial derivatives chapter is that things are weird in calculus 3. And this gives me a chance to show you some weirdness here. I got del x del theta, del x. In calculus 1, you got stuff like let's see, y equals log x. So then dy dx equals 1 over x, right? And what if you wanted to do dx over y? Dx over dy? Is that the same thing as just inverting both sides?
You could solve for x.
You can solve for x.
And then take the derivative.
Alright, so if I solve for x, I get x equals,
E to the y.
and the derivative is
E to the y.
e to the y. And if I invert 1 over x and get x over 1, what's x? E to the y? Oh, yeah, same thing. So in calculus 1, it's okay to turn these things upside down. You might have to make a substitution, but it's going to come out perfectly. And that's the stuff that's behind the formulas for taking the derivative of an inverse function. You know, logarithm is inverse exponential, and arc sine is inverse sine, and all that stuff. So let's try it here. Let's do problem 5, we had an x theta combination. In problem 8, we had an x theta. In fact, I didn't even do the one with y. But anyway, so let's see. They're both negative. That's a good thing. So what about it? Let's convert this answer into polar coordinates. And by the way, problem 9 says compare your answers for del x del theta in problem 5 and del theta del x in problem 8. So I did all of problem 5, I've done part of problem 8, and now I'm going to talk about problem 9. So anyway, what if I just turn this number 8 answer over? What if I have del x del theta equals x squared plus y squared? Actually, I want to turn the other one over. That makes more sense. So I've got del x del theta equals r negative 1 over negative
r, or negative 1 over whatever.
Negative 1 over r sine theta. And now I want to switch it to the other coordinate system. So in this case, let's see. Y is r sine theta, right?
Yeah.
Okay. So I've got minus r sine theta. And what's x squared plus y squared?
That's r squared.
That's r squared. You know, I agree with you.